Geeks Cocktail. Part 3. Aerate Principles, Microbubble, Swirl Flow Method. In this video, the principles of aerate, microbubble and swirl flow method are explained with experiments. As for aerate, bartenders disagree on whether it's dissolution or microbubble. If aerate is dissolution, it means that the air is dissolved in the liquid. In the case of microbubble, air is made into very fine bubbles and taken into the liquid. Consider whether air can be dissolved into the cocktail ingredients. The solubility of air in water is expressed as solubility. The slide is a pie chart of air component ratios and the solubility of the major components of air. As you can see from the slide, most of the air is made up of components that are very sparingly soluble in water. Therefore, the solubility of air is as low as 0.029, making it very difficult to dissolve air in water. Let's check the state of the liquid before and after the actual shake. The slide shows the state of the liquid before and after the shake, taken with a light sheet using a laser beam. In the experiment, we use green tea in PET bottles. The left side of the screen shows the image before shaking and the right side shows the image after shaking. On the right side of the screen, a large number of microscopic bubbles are shown as white dots, confirming that the meaning of aerate is to incorporate microbubbles into the liquid. In the experiment on this slide, normal lighting is used instead of a light sheet, and magnified images are taken with a microscope. In the previous experiment, what appeared to be a white dot can be confirmed to be a microscopic air bubble by taking a magnified image. In addition, the movement of the bubbles is not only surfacing from the bottom to the top, but also moving up, down, left and right with the flow in the glass. From this, it can be seen that the buoyancy of fine bubbles is very weak. Taken together with the previous experiment, we can determine that one of the purposes of the shaker, to aerate, is to incorporate microbubbles into the liquid. Why can microbubbles stay in the liquid in the glass for a long time? This is because the speed at which bubbles rise to the surface is significantly slower, about 1/2000 th of that of millibubbles, which are bubbles visible to the naked eye. In addition, most microbubbles have negative potential, so microbubbles do not merge with each other. Therefore, the bubbles do not become larger and do not increase the speed of surfacing. Let's think about where the air that is the source of the microbubbles created in the sealed environment inside the shaker comes from. There are two possibilities. One possibility is that air dissolved in the cocktail ingredients was released into the liquid as microbubbles. Another possibility is that the air inside the shaker was drawn into the liquid as microbubbles. Two conditions are required to turn air dissolved in a liquid into microbubbles. One is that air is dissolved in the liquid by pressurization. The other is to rebubble a liquid in which air is dissolved by depressurizing it. There is a theory that the ultrasonic waves generated by the shakes generate microbubbles. This is thought to refer to a method called ultrasonic cavitation, in which microbubbles are generated using the decompressed state generated by ultrasonic vibration. Experiments will confirm whether ultrasonic cavitation can generate microbubbles in cocktail ingredients. The glass is filled with dry gin, which is often used as the main ingredient in cocktails. Observe the state inside the glass by light sheet photography when ultrasonic waves are applied to the glass. As the experiment shows, no air bubbles form in the dry gin in the glass. Cocktail ingredients typically used in shakes are stored in an environment of 1 atmosphere. Since this does not satisfy the first condition explained earlier, air must be dissolved in the liquid due to pressurization, it is an expected result that bubbles are not generated by ultrasound. Let us confirm by experiment that rebubbling occurs when the condition of air must be dissolved in the liquid due to pressurization is met. The glass is filled with carbonated water in which carbon dioxide is dissolved in water by pressurization. As before, we will observe the inside of this glass by light sheet photography when the ultrasound is applied to this glass. As the experiment shows, rebubbling of dissolved carbon dioxide occurs when ultrasound is applied. Since cocktails made by shaking do not use ingredients that have air dissolved in the liquid due to pressurization, the microbubbles generated by shaking are not generated from the cocktail ingredients. In order to capture the air inside the shaker as microbubbles, it is necessary to create a swirl flow between the air inside the shaker and the liquid cocktail ingredients. In the vortex created by the swirl flow, large bubbles are stretched and then sheared, which breaks them up into smaller bubbles. By repeating the splitting of air bubbles by this shearing, the air bubbles inside the shaker change into microbubbles. Experiments will confirm whether microbubbles are actually generated by swirl flow. In the experiment, an electric creamer was used to generate a swirl flow. Inside the glass, as in the first experiment, is a green tea of PET bottle. The agitation by the electric creamer generates a swirl flow vortex, which shears the air taken into the liquid into fine air bubbles. Supplement about using electric creamer to create microbubbles. Shakes and electric creamers use different air sources for microbubbles. It is the difference between the air in a sealed environment and the air in an open environment. Due to this difference, it is thought that the generated microbubbles also have different scents and temperatures. Regarding the use of electric creamers, it is recommended that consideration be given to whether the method of making microbubbles is appropriate for the cocktail to be created. This slide explains how the swirl flow inside the shaker works. A swirl flow is a flow that has components in both the axial and rotational directions. Rotational axial flow is the forward-backward flow inside the shaker. Rotational flow is the flow that whirls along the inner surface of the shaker. In other words, flow in the front-back direction only is not a swirl flow. To achieve a swirl flow inside the shaker, a vortex flow along the inner surface is required in addition to the back and forth flow. In this video, we explained the principle of aerate. We explained with experiments that aerate means taking microbubbles into a liquid. We also explained that the air that generates the microbubbles is the air that is sealed inside the shaker. We also explained that in order to turn the air inside the shaker into microbubbles, it is necessary to generate a swirl flow by shaking, shear the bubbles by the swirl flow, and divide them into fine bubbles. The next video will show the movement inside the shaker. The movement inside the shaker will be illustrated with experiments using transparent shakers and slow-motion photography. If you are interested, please subscribe to the channel and watch.